In this video, we will compare and contrast deterministic versus stochastic optimization. Much like the distinguishing between whether continuous or discrete optimization, distinguishing between deterministic and stochastic optimization has to do with the nature of the provided data. To be able to distinguish between the two options, let us first refer back to our discussions of continuous or discrete optimization. As we previously stated, in both continuous and discrete optimization, there is often a reliance on each other to overcome the other's failure points. Continuous optimization relies on the discretization of continuous functions, with the behavior between each element of the continuous set known. Likewise, discrete optimization relies on assuming the behavior between each element of the set to be known, and continuous. In both of these instances, deterministic optimization is used because we can assume that we can trust the data that is being used. However, what if the data used cannot necessarily be trusted? To understand the effect that any sources of error can have on the solution output, let us take this simple curve and propagate the error, like so. As you can see, the actual process described by the data could take on any value within the shaded region. So we cannot assume that our values are completely accurate. In these instances, we use optimization under uncertainty, or stochastic optimization, to account for different sources of error. In the use of stochastic optimization, the discrete or continuous function is replaced by a set of random variables governed by a probability distribution of some sort, like a normal distribution. Using the random variables and probability, an approximate solution can be extrapolated from the randomness. Though it is most ideal to be able to assume the data takes on a deterministic nature, the reality is that most, if not all, measurements of physical processes will entertain a little randomness and error. This error-inducing randomness can come from other environmental effects that the mathematical model does not account for, or from something as simple as measurement error when the data was accumulated, to something as complicated as attempting to predict the results of different processes in the future, such as in disease modeling and financial technical analysis. The question of whether or not you would use deterministic or stochastic optimization is mostly dependent on how much you believe that the data errors would impact the feasibility and optimality of the output solution. For simulating physical processes, the accuracy is dependent on comparing previously accepted results to your experimental results. For predicting future processes, the accuracy can depend on previous behaviors of the process for which you are trying to predict. Thank you for watching this video. See you in the next video.